Hello everyone. My name is Abhiram Modak. Uh, I am a retired professional from the software field, and I'm going to present over next few lectures or videos. This is what I'm calling up as bottom-up theory. Now this is a strange word, but I'll try to unbundle it as we go ahead. So some background. So I'm an engineer by education, not a physicist or anything like that. But I have a keen interest in physics, and I have been doing my own research, my own thought experiments for last many decades, you may want to call, right from college days, really. So, uh, so this bottom-up theory is a synthesis of all those things, and it is still going on. It's by no means complete, and probably it will not complete for my remaining lifetime. But let's see. So I'll try to explain what I have come up with and what my thought process is. And again, this is really for physicists to take cue from and then take it ahead. So I'll be presenting some formulae, some equations, something like that. But essentially, it's not in the form of a paper or for a scientific journal or anything. This is just a thought, and then I thought it was interesting, and I thought of sharing with you all. Okay, having said that much, probably let's get into it. So now, what you see here is the whole gamut of things that we come across in various forms, in form of a mass or a particle or a field like an electromagnetic field, or if you are more keen reader of things like gravity and all, you must have read about space-time curvatures and things like that. And of course, you have your electromagnetism, which is also there for last more than 100 years. So look at this diagram more like a, what do you say, a mind map, not really a pure hierarchical things I mean arranged in a hierarchy. So on the left hand side, if you see, you think of large bodies like you and me, and then planets and universe and whatnot. Then we come to a level where it is molecule, and then you have atoms, then you have subatomic particles like electrons, and then now you also have subatomic particles, if you want to called quarks. And then there is a string theory which is still below that, which is being proposed but not yet proven. So if you really see the way this thought process is going on is always top to bottom, and then I'll come to the lateral part of it. But you people thought molecule was the biggest thing, smallest indivisible thing. Then we came up with atoms, and then you have subatomic particles like protons and electrons, and then quarks, where typically three quarks will make one subatomic particle, and now below that string theory. So it's largely, if you want to call it, an observational journey, meaning what more would be there would be observed. So as our observation progressed, our knowledge of these particles progressed. Okay, so we went always one level below of all that, of what we knew earlier. On the right hand side, you'll see a lot of other things, right? So which kind of play into this left hand top to bottom approach. So then on a parallel track, you have this quantum physics, right? So where it is purely observational, uh, hardly anybody really understands quantum physics, but everybody can observe it, everybody can write formulae for it, and everybody can work with it, but really not understand it. Then of course you have this classical electromagnetism theory, which is essentially in form of waves and things like that. So uh, So that was the oldest theory in terms of energy. Uh, then later came quantum, and then you have photons where light is a particle as well as a wave. So I've just put it in between over there. And then on the right hand top, you have this all encompassing thing called gravity, which is earlier it was Newtonian, and then you have Einstein's general relativity, which then we came to know that it was all really a space-time curvature and not really a force. But on the sidelines, you also have these things which are still quite elusive, which are called as dark matter and dark energy. So dark matter is supposed to contribute to gravity, overall gravity of the universe, and dark energy is supposed to contribute to alternate repulsive force in the universe. So this is really what we know so far, and how people have been thinking. And then, so this is, I'm just calling it a gamut of mass, field, space, time, energy, whatever you want to call. So that's really the whole mass energy thing I have tried to capture in a single mind map, if you want to call it. So in the last slide, we saw the gamut of all things that are either mass, energy, force fields, space-time curvatures, whatever. And then we also said that it is largely a top-down approach, all based on observations. And I mean, that's how physics and generally science has progressed, right? So what is observed becomes the gold standard. Now here, now let us come to what I'm trying to say. Okay, so what I'm trying to come up with is really a bottom-up approach, and hence I'm calling it a bottom-up theory. So my thought process is like, if there was to be a fundamental quantity, right, like say mass, or even space, or even time, what it would be really. So it's a complete reverse approach, saying that if, for example, if there was a particle, how it would be. So my simple assumptions would be, it would have mass and it would move in space. That's about it. So no charge, no nothing, right? And then this bottom-up theory will somehow will have to define all those things in course of time, right? So I started really at the very beginning, in the sense I started with nothing. So when I say nothing, it's really nothing. So there is no space, no time, no mass, no energy, nothing, no universe, if you want to say. And then from nothing, maybe space came up first, then there were rest mass, and then there was motion, and hence we got the idea of energy and time and so on and so forth. And then if you see, I'm going bottom up, and then you see the three dots after energy. So what it really means, or what I want to say here is, maybe there are a few more levels before I can reach, say, quarks or strings. Okay, and hence once I reach there, probably the portion above that, which is subatomic particles and then atoms and molecules and so on, that is already well defined, right? So if my theory was to hold good, then it should start from the bottom, which is nothing, and then it should reach these things like quarks or subatomic particles and so on. Not only that, it needs to, it really needs to define a lot of other things also, if this was really a worthwhile theory to go after. So I'll cover that in next slides, but essentially my approach here is that we start from nothing and then we define space, we define rest mass first, then we define motion, and hence you also have energy, and then of course time incidentally has a uh, what do you say, time is at the denominator of the energy definition itself, so time will automatically be defined there, and then so on and so forth. You may have some more intermediate particles which will finally rise up to the level of quarks, and if string is there, then that will be before that, and then quarks and so on and so forth. So this is a gigantic task, and then also very radically different way of thinking, rather than go the observational way, which is top to bottom, and we will see how much I have progressed. So I have progressed a bit, but maybe there are lots and lots of things that need to be taken care of. So we will see in the further slides. Okay, so as I said in the previous slide, that if this bottom-up theory has some value, then it needs to really define a lot of things. I did mention the particle physics part of it, where uh, this theory needs to really go from bottom up till to the level of strings and quarks, and hence then the other particles are already defined. But that is just one part of it. This theory really needs to define many other things. For example, it should define dark energy. It should define dark matter, right? It should define space-time. So I did mention space and time separately in the previous slides, because we said we'll first start with space and then time will get added on later. But essentially the concept of space-time and its curvature and hence gravity, uh, it all needs to define that, right? Separately, large body physics, what you and me always observe in our daily lives, that also needs to be there. Then there are some things which are probably not in the purview of physics per se, but I have just mentioned them. If you see on the left hand side, I mentioned memory and observation. Okay, so why I have mentioned that is specifically because, see, this whole view of physics or universe is from a human standpoint, in the sense, when we say observation, it is inherently a human observation or an observation done by a machine invented by a human, right? Also, when we say observation, there is an inherent assumption that the human or the machine does have memory, right? So what is really all this, right? So the view of universe comes from these two fundamental things, the observation and memory, right? So if I don't remember where I started counting time, then I won't be able to observe anything, right? So if I don't know the zero of the clock, I won't be able to measure any interval and probably may not be able to measure any quantity. So that's why I mentioned it over there. So it also has a angle of quantum physics to a certain extent, but we'll visit it later. And then beyond that, we really go into a kind of a metaphysics world, if you want to say. So where you have this thing called ego, right? So, and then ego is a very broad term. I don't want to spend too much time on it, but essentially there is ego and hence there is life. Okay, and hence that's why we are observing all these things, and hence there is this view of our universe. So I've just mentioned it over there. On the right hand side, you will also see certain things which are still not proven by any means. So especially this faster than light particles, right? We all know special relativity will always say that nothing can travel faster than faster than light, or at least information cannot travel faster than light. But are these particles really there? And if they're there, can the bottom up theory really define them in some way? Okay, so all these things uh, we'll need to cover. And then, as I said, this is a gigantic task, a very radically different approach of how really we look at the universe. And let us see how far I really go. And then, as I said earlier also, so these are just concepts. At some places there are formulae, there are some proofs, but it is largely a concept, and I would really expect all the physicists and scientists of the world to take this forward. Thank you. So, let us start with space, and I will divide this concept of space into three parts. So, this is part one, and then I'll end my this particular video at the end of part one, and then I'll add subsequently more videos on space and also motion and time and all the things after that. Okay, so as I said, I started with nothing. Nothing means really nothing. No space, no time, nothing. No mass, no energy, no force fields, nothing. So my idea is like this. Out of nothing, which you can say zero or shunya, came equal quantities of real space and imaginary space. Okay, so I've just shown over here in a representational way. On the left hand side, you will see this white and gray, which is real space in the way we look at this space, right? Where there is real length, breadth, and height. So I put it as x, y, and z as the coordinates for this volume V, I'm calling. And then on the right hand side, it is the imaginary space. In the sense, the each of those length, breadth, and height are imaginary, in the sense that Ix, Iy, and Iz, and hence the volume is Ix into Iy into Iz. I mean, generally minus Iv. Okay, where I is the imaginary number. Now, so imaginary space, I have shown it in blue and the real in white and gray. So the idea here is that out of nothing came equal quantities of real and imaginary spaces. And will it be a cube? May not be, not necessarily. It could be a sphere, it could be anything. But the whole point is the quantities were equal, and the square of these volumes, if you add, will give you really the, what do you say, the zero or nothing, right? You will get back your nothingness, if you want to call. So that's really my fundamental starting point, where I say space came out of nothing in equal quantities of real and imaginary volumes, and if you square those volumes and add them, they give you back nothing, which is zero or shunya. Okay, so I already said this, that space came out of nothing. Real space and imaginary space came out in numerically equal quantities, and hence If you add the squares of them, you get back 0, right? So I've shown here an overlapping space where, I mean, the same area. So by the way, this black background is representing nothing, right? So nothing should be really nothing, single dot, but not really helpful to represent things. So the black background over here, I'm saying it is nothing, and then there are these volumes of space which are equal in quantity, but one is imaginary and one is real, and here they are like completely overlapping each other. Okay, so the way we said the space was created, it should disappear also, right? So nothing could stop them from these both the cubes from merging and disappearing, so as to say, or destroying themselves. So as long as these two cubes, they can come together and they can really disappear, right? So is what really makes them disappear? I don't know, or at least at this point in time. But mathematically, it will it can just go away, right? So it was there, but equal and opposite quantities of real and imaginary spaces came together, and they can in theory disappear. The way they can appear, they can disappear. Okay, so so this is really what we just said, and on the right hand side, I've written those x into y into z as v, the real space volume, and then ix into iy into iz as minus iv. And then if you square these quantities of v and minus iv, and if you add them, you get 0. So you get back nothingness, right? And this expansion and, I mean, the creation and destruction of space has got a lot of ramifications, as we will see later, especially in terms of gravity and anti-gravity and things like that, and also masses. When we define them, they will have some inherent velocities and things like that, but we'll visit that later. But essentially, at this point in time, what we are saying is space can appear and disappear from nothingness or into nothingness. The only condition is they have to be in equal quantities in the imaginary world as well as the real world. That's all we are saying. Now, when they appear or disappear, right, if they want to disappear really, so do they overlap, or are they completely separate, or they they completely overlap, or they partially overlap, or they're completely separate? We don't know, right? It may be all of these, or we don't know really. But as a teaser, what we can say is that on the left hand side, where you have the complete overlap, what it means is if I have a real mass, then simultaneously it will be there in real space and imaginary space, and that has got again a lot of ramifications. So we will go there. The second one, which is like those two real and imaginary spaces are different, right? They don't have any overlap. So this may have a conclusion that these two worlds are completely different. We cannot communicate, or we really cannot do anything with each other, or we even don't know whether the other world exists, right? And then there is a in between condition, which is the third on the right hand side, where there is some overlap, and then there would be things which would be observable when we actually go to that observation level. We are very far away from that right now, but certain things would be observable, and then suddenly they will disappear because they would go into imaginary space. So all those things we will visit them later, but for the time being, what we are saying here is space can get created or destroyed as long as it is in equal quantities in the real and imaginary world, and there could be uh, overlaps of these spaces, a complete overlap, a zero overlap, or a partial overlap. So let's digest this, let's think over this, and in the next video I'll talk more about these spaces. Thank you.